Okay, hello everyone. Today I'm going to explain the differences between bagging and boosting and their most common implementations, which is random forests for bagging and XGBoost or other implementations for boosting. Okay, as you remember from class, I'm gonna rush a bit through the bagging part. Okay, bagging means that you're going to take different samples from your training set, okay, random samples. You will train a single decision tree with each sample, and then you will average the predictions from all of your trees, okay? This, um, this reduces the variance from the single trees, which, as we know already, when the trees grow up to as much as they can, they will create super pure leaves, thus increasing the variance. Okay, so we can reduce this variance by taking the random samples, or which is called bootstrapping. Okay, and then if we aggregate these predictions, this is called bagging, bootstrap aggregating. Okay, you can see here that when using bagging, we are smoothing the surface in the prediction, meaning that we are reducing the variation in each region. Okay, you can see, in fact, that in this case, the border of classification is way more smooth, and it doesn't have this overfitted regions in which there is only one observation. Okay. Let's now dig a bit deeper into the concept of bagging, okay? And let's kick it up a notch. If we not only take samples on the rows of our data, but also we take different samples on with different amount of features, meaning the columns, this is how random forests are implemented. Okay, so in each one of the samples that we take a random sample of the rows, plus we are taking a random sample of the columns or the features. Okay, usually this number of features that we are going to use is called m. Okay, that should be lesser than the total amount of features, and in fact, by default, I think in scikit-learn, the default value for random sample of features is the square root of the total features. Okay, so by using this technique, we will decorrelate the trees because each tree will see something different and will learn from something different. Yet, when averaging their results, their predictions, we will still be reducing the variance. Okay, so let's move on to boosting. Okay, boosting is another type of ensemble model. Okay, and as you know from the previous minutes, when we use bagging, we are basically taking different samples at the same time, and then we are training one tree per sample at the same time. Okay, so we are taking one tree with this sample, another tree with this other sample, another tree with this other sample, and the three trees in this case will be trained and they will predict at the same time. Okay, the concept behind boosting, on the other hand, means taking one tree. Well, it's called a stump because it's a very basic tree without many splits, training that very simple tree, that very dumb tree, on the total data set or on a sample of the data set, as you prefer, okay? And then with the prediction of that very dumb tree, you calculate the residuals, okay? And then you train another tree in order to predict the residuals, okay? Basically, what we are doing is to create a sequence of trees where each tree will learn from the mistakes that the previous tree made. Okay, using the same analogy as I used in class of giving each one of you a different sample of the exercises from the exam, and then averaging your results. The equivalent analogy for boosting would be, let's take each one of you from class, okay, and I will examine each one of you in private, okay. After each one of you is examined, you go out, okay, and then you tell to the next student, to your colleague, what were your mistakes, okay. So now your colleague knows what not to do. So then your colleague comes in, gets examined by me, and then I let them know the mistakes they made and go out and they tell the next student and so on. So that way, each student will learn from the mistakes from the previous student, and in a way, after some students have taken the exam and have learned from all the mistakes in the past, there will be a student that will pass the exam, or even better, that will nail the exam. Okay, this is what we are trying to achieve with boosting. Okay. So in the main tuning parameters that we can control in boosting, we have the number of trees, okay, which is how many students will be examined using the same analogy, okay. The shrinkage parameter, this is also called the learning rate. Um, this represents, let's say, how smart is each student, okay? So in order to achieve a good result, we could have just a few very smart students or a lot of students more on the dumb side, okay? In the end, there's the balance in between how many students or how many trees and how much each student learns, or how high is the shrinkage parameter or the learning rate of each one of the trees. Okay, okay. And then of course, since we are talking about trees, we can use regularization in our trees. We can control the number of splits, the minimum samples in each leaf, okay, and so on. So this is the concept behind boosting. As you can see here, there is a graphical representation on how each tree is going to be learning from the residuals of the previous tree. Okay, you can check that the out of the data, okay, and the prediction, okay, we can create the residuals, okay, and that would be the training data that will be a part of the training for the next tree, okay. In the end, after a certain amount of trees and learning, our final prediction will take into account all the mistakes that previous trees made, and the final prediction will fit the data better than the original prediction or the first prediction. Okay. One of the most common implementations of boosting is called XGBoost. Okay, it's the one I've used the most and the one I'm more familiar with and more comfortable with. But there are many implementations. Okay, you have XGBoost, you have Light GBM, you have Cat Boost. So there's many of them. All of them with some differences, but behind each one of them you have the same concept. Okay. So the pros of using boosting, okay, it's super fast if you use parallel computation. It's super efficient as well, okay. It's super versatile. You can use it for classifying, for regression, or even for describing a situation, okay. Even for you can, let's say, overfit an XGBoost algorithm into fully understanding a problem, okay. And then after the prediction, you would understand that problem, okay. Just like with any other classification and regression tree based model, we can use boosting in order to extract variable importance by using, for example, the feature importance of the last tree, the tree that has learned the most from the previous mistakes. Okay, and one of the major pros of XGBoost or boosting in general is that they do not require feature transformation. They deal really well with missing data, with non-scale data, with non-normalized data. So it's basically a super machine where you can fit almost anything, and the results will be super good, and you will have the results super fast. Okay. Of course, the con here is that it will lead to overfitting if you don't tune your parameters well. Okay. This the main or the first way that or yeah the main way in which your XGBoost stance can overfit is if you include too many trees, too many students. Okay, the trees or the final tree will have learned so much from the original data, from the training data, that it will be very difficult to generalize in the future. Okay, with unseen data. But one of the cool things of XGBoost or gradient boosting is that you can control one of the parameters, which is called early stopping. Okay, and with early stopping, you can control until how many or the number of trees at which the training will stop, okay, or the iteration will stop. As we have mentioned many times, we can check, we can measure the complexity and the error, for example. Let's check the MSE. In our case, the complexity will be represented by the number of trees that we keep adding to the queue of students, remember? So if we check the complexity, if we increase the complexity and we check the MSE in every step in which we are increasing the number of trees, we can see that on the training data, the training error will follow this curve, okay? And as we already know, if we check the same error but on the test data or on the validation data, we will see that it will reduce at first, but after a certain point, it will start increasing, okay? What this tells us is there is an optimal point of training, an optimal point of complexity, an optimal amount of trees that we should add for this problem in order to not overfitting, okay? This region here is overfitting. And if we stop adding trees at this point, we will find an optimal amount of trees in our model. Okay. So in the slides that I shared with you the other day, you have additional resources here. Okay. And this, I would say, this is the take-home point and the comparison between bagging and boosting, which are the two main ensemble models for classification and regression trees. Okay, remember that random forest is not an iterative process. We basically take one sample for each tree and we train each tree at the same time, and then we average the predictions. Okay, by doing this, we reduce the variance from each individual tree. Therefore, we are reducing the overfitting at first. Okay, even though that random forests can and will overfit as well if you don't control the size of each individual tree. Okay. On the other hand, we have boosting, which means training a very dumb tree or a very simple tree, a stump, with the training data, okay? Then calculating the error or the residuals between the prediction and the actual target, okay? And then we use another tree, which will be a bit more complex, okay? And this tree will learn from the mistakes from the previous tree. This way we keep adding trees and we keep adding and adding with the hope that each tree will learn and will internalize the mistakes from the previous trees. Therefore, the prediction of each consecutive tree will be better than the previous one. Remember that we should only increase the number of trees up to a certain point in which we will start overfitting. Okay. So this is the explanation of boosting and how it's compared with bagging. Okay. And this is something that you should take into account for the asynchronous class on classification and regression trees. Okay. Thank you very much and good luck with the assignment. Well, the asynchronous.